or if you buy Tesco burgers, you're eating a horse. That's a different matter. Okay? But you are that shape. You've got a large head because you want to think, because you've decided that rather being something that like a cheetah or whatever that chases after animals and kills them, I'm going to be something with a large head that can allow me to think, that means that I can develop a gun, that means I can shoot it, that means I can then eat it. Right? So you are your shape, you've got a large head in relation to, or large head that allows you to have a large brain that allows you to be able to be clever and to shoot things rather than chase after them. So, you are your shape because of that need to acquire energy to stop disorder occurring. So we can think, here is an ice cube, and here today, on this very cold day, we see ice cubes around. They have minimum entropy, maximum order. There is a crystal structure, the order of those different molecules, water molecules within that ice structure is very ordered. There is minimum entropy, maximum order. Whereas, when it warms up, we go to a puddle of water which effectively has no structure, the molecules can move around, there is maximum entropy, much more disorder in that system. So, we ask the question then, how we're going to get this energy. We need to be aware then of metabolism. And metabolism is all the chemical reactions that are going on in an organism. So whether it's you, or a bacterium, or whatever, those chemical reactions of metabolism. And it's split into two basic sorts of reactions. The first ones are catabolism, breakdown reactions. You are carrying out catabolic reactions at the moment. Anybody who had breakfast is breaking down those foodstuffs. The reactions that break down foodstuffs that are taken in. But importantly, and we think, oh, we get energy from them, we do. So these reactions release energy, but they also release simple, by which I mean a small number, about 12, 3 or 4 or 5 or 6 carbon compounds that produce everything else in the cell. So there's a small number of very important compounds that are used as the starting point for making everything else in the cell. So, they produce energy, these simple compounds, and also reducing power. And we know reducing power are electrons. So we know that you can either have reduced or oxidized, and if we can reduce things if we've got electrons. That's what we want. So foodstuffs really provide 3 things. Energy, these simple compounds, and electrons. Because we're going to, for you, are using all those now. When you're making things in the body, what you're doing now, are the reactions of anabolism. All the biosynthetic reactions used by a cell to make new cell material. You are made of DNA, RNA, proteins, lipids, polysaccharides, etc. All your cells are made of that, you're made of lots of cells. So to make those large molecules, you need those anabolic reactions to make new material. And so the reactions use the energy, the simple compounds, and the reducing power that are released in catabolism. So the reactions of catabolism release energy, the reactions of anabolism take that energy and those other things as well and use them to build new cell material. So, catabolism and anabolism are the things that we've mentioned so far. So to grow, cells need energy, precursor metabolites and reducing power, electrons. And these two things are linked. Catabolism and anabolism are linked together. The reactions of catabolism, these breakdown reactions, drive the reactions of anabolism. So catabolism, those breakdown reactions, are degradative, they are oxidative, you oxidize those materials, they yield energy, they use a variety of starting materials. Who had breakfast? Yeah, what What did you have? What did you have? Leftover pasta. Okay, that's not a normal response we get. Who else had breakfast? A banana. Leftover pasta and a banana. Right? Then, anybody have toast? Right? Toast is another. You take in a variety of starting materials that you use and break those down. But it has well-defined products. We said that there are about 12 very key small molecules that are important in driving, in getting those molecules that we're going to use for anabolism. Can we try and get here on time, please? But those reactions use these compounds. Doesn't matter if we know what they are, because we will do in a little while, but they use these compounds NAD, which stands for nicotinamide adenine dinucleotide, or they use NADP, which stands for nicotinamide adenine dinucleotide phosphate. Okay? So NAD, NADP are the reaction, or the compounds that are used in catabolism. Whereas anabolism, the biosynthetic reactions are synthetic, they're reductive, they need electrons. Okay? So if we're going to carry out an anabolic reaction, we tend to want electrons. A few years ago, I was given some electrons, right? A student was fed up with me throwing things at them. So she bought me a present. She said, I've got you a present. I thought, is it a bottle of wine? Trip to the theatre? Whatever? No, some juggling balls. Right? Because she was fed up with me throwing things at her. Right? And then, so we go and move. Go and sit somewhere else. Right? So, what we'll have, anybody, I warn you now, anybody close to the front will be receiving electrons, right? And I want them back. So there are 3 electrons that we've got. So we need these electrons to carry out reductive reactions. It requires energy. We need to input energy into these processes. I want my electrons back. I need this. 1, 2. Some reactions are quite slow. Where is it? We'll go and get it then. Thank you. Right. So anabolism has well-defined starting materials. This small number of compounds that are produced, these 3, these 4, these 5, these 6 carbon compounds that are produced in catabolism, but these reactions use NADPH, the reduced form of that cofactor NADP. So the oxidized form is NADP, the reduced form, when it's got electrons attached to it, is NADPH. So anabolism uses NADPH, those biosynthetic reactions. Catabolism uses NAD or NADP. Primarily NAD, but both can be used. So, with regard to thermodynamics, and we'll just briefly touch, 10 minutes talking about thermodynamics, but the important things that we have in a biological system, i.e. you, or a cell, or whatever, when looking at the energy changes in whatever system we're looking at, there are various things we need to measure. The internal energy, first of all, the total energy of the system. If this system is this room, total energy, what's in this room, right? The total energy in the room, that's one thing. Enthalpy, the heat content. And I don't just mean what the temperature is, but how much of that energy is heat. Because there is other energy in this room. What other energy do we have? Light energy, other energy, sound, right? So within this room, yes, there is heat energy, we're a certain temperature, but there is also light energy, sound energy, there might be kinetic energy. Give me some kinetic energy. Yeah, you know, you can move around. All those things. There's not much kinetic energy at the moment, but all those different forms of energy contribute. Entropy, the degree of disorder. 10 minutes ago, the degree of disorder was increasing in this system. The entropy was increasing when I'd gone out. Because I'm now putting some energy in, there is not much disorder going on. Okay? So the entropy is quite low at the moment. But the important one from a biological point of view is called the Gibbs free energy, the energy available to do work. And it tells us how much energy is there within the system that we can get out of the system to do useful work. That's what we're interested in, the Gibbs free energy. And the person to blame for that is Josiah Willard Gibbs, who is there. So he thought of this idea of Gibbs energy. And we look at changes in these factors. So all these changes in energy levels, etc. And we measure the initial state compared with the final state. The actual values of these things can be difficult to measure, but we can much more easily measure changes in these values. So, delta G, the one we're interested in, delta G is the final Gibbs energy minus the initial Gibbs energy. It's the change in that Gibbs free energy. So delta G, delta meaning the change in, that triangle symbol, the change in Gibbs free energy, is a measure of the amount of energy potentially available to do work. How much energy can we get out of the system? The more that Gibbs free energy is, the more work we can do. And you know, it doesn't matter what all these relationships are, but all these things, the energy, the entropy, are all linked. There's a relationship between some of these. For example, delta G equals delta H minus T times delta S. So what that says is that the delta G of the reaction depends on the internal energy of the system and the change in entropy of the system. How much change in disorder has there been? So it doesn't matter what the other relationships are, but what we're saying is the amount of energy we can get out of the system depends on the internal energy and the change in entropy, change in disorder. Because we saw when I left the room, the degree of disorder went up, but there was much more energy, much more sound. I heard it outside. You know? I didn't come back in till I heard it. So you can see that the energy available when there is a change in entropy, there is energy available. So free energy is related to the total chemical energy of the system and hence to the chemical stability of the system. So if something is stable, for example, we can get a change in the energy level. So let's take here, right? Here is an energy level there, and there's another energy level there. Let's do it with a rule. And so when there is a change in energy level, if we're quiet, energy level there, so energy level down there, that's there, and it just goes, energy comes out. We hear it. Do we hear it? We hear it, yeah. So there's a change in the energy level, from there down to there, energy is released, and you receive that energy. You heard it. Energy is released. But that was all very well there, but let's do the same again with this, up there. It's not doing very much. It's not very stable, it's there, it doesn't need very much to do anything to it, right? If we have free energy is high, we have a potentially unstable system, and the system will potentially go to a lower free energy level, as we saw with the rule note that this says nothing about the rates at which these reactions will occur. If we leave that there, it will stay there unless we put in some activation energy to get it over that activation hump. And we get energy out. So it didn't hit the ground as hard, it wasn't as noisy, and it wasn't as heavy as that, so we didn't get as much energy out. But that was potentially unstable, but how quickly it goes to the lower energy level depends on starting the reaction off, putting the activation energy in. So if delta G is negative, energy is released from a reaction. So if delta G is positive, so that's the first thing to remember. Delta G negative, energy is released. Delta G is positive, the system is energy requiring and is thermodynamically unfavourable. So this, for example, does not go from there up to there. Jump. Get up there. It doesn't do it. Right? It's not going to go to that higher energy level. But how can we do this? Energy liberated in energy releasing reactions can be used to drive energy requiring reactions. Okay? And so the reactions are said to be coupled. So we need a volunteer. You'll do. Thank you for volunteering so rapidly. But what we're going to do, we're going to be biological. Here is a protein. You are a protein. And proteins are made of amino acids which make up a peptide chain. So here is a peptide chain. And this is where it's growing, right? Here. So you can be you're a peptide chain, right? I need to hold that there, out like that. Because here is an amino acid. Right? That's an amino acid. And where do amino acids go? On the end of the peptide chain. So, that, when I said jump, jump. Isn't it? We've got to put some energy in, and our energy coupling mechanism of doing this is here, a ruler. Right? I normally borrow a ruler, but then we got a ruler. Yeah. But the trouble is, when you borrow a ruler like this, it breaks. Right? I've broken about 20 over the years, student rulers. So that's why we've got this, a metal one, and so it doesn't break. And it has the advantage, if anybody talks, I can go across the knuckles. So what we want to try and do is have an energy releasing reaction that's coupled to an energy requiring reaction. And adding on that amino acid onto that peptide chain is what we're going to try and do. Okay? So this is what we're going to do to try and couple these two things together. Okay, that if we put that there, we're going to release some energy, and my hand is going to come down like that, and that is the energy releasing reaction, right? This couples the energy to the energy requiring reaction, is that this will go up and land there, and land on there. We're going to release some energy. Are you ready? Are you ready, yes or no? Alex Ferguson doesn't go, are you ready to Rooney? And, and he goes, oh, no. Are you ready? Right. So you see what's going to happen, right? Energy is going to be released. That's going to then couple, give the energy there to that amino acid that's then got enough energy through a ribosome or whatever to link the protein down. Everybody with it? What are you going to do? I don't know. Go try. Go to the other side of the table. Go to the other side of the table. the other table. You ready? Yeah? Yes? Yeah, you ready? Sure? I can't see this going on. Probably about there. You've got to catch it on the end. That's what you've got to do, catch it on the end. Oh! So close. But you get the idea, you know, this is misreading, this is an antibiotic has affected protein synthesis, right? But the idea was there. That's probably about the closest I've ever got it. But we get the idea of that would then add on to there, and we added the next amino acid on there. The point is about energy releasing reactions being coupled to energy requiring reactions. That's the point we're trying to make. So as biologists, we're interested in what's called the standard Gibbs free energy change, measured at pH 7. Because normally with these things from a chemical perspective, they are measured at molar concentrations. We want this at pH 7. So that's the important thing. And the units of this standard free energy change are kilojoules per mole. So that's the units that we get, kilojoules per mole. And delta G naught prime, what's called the standard free energy change, delta G naught prime, as biologists, that's what we want, can be calculated from the equilibrium constant. So when the reaction goes, when it reaches equilibrium, the change that you've got to start with in the end in the thing from that equilibrium constant, we can work out what delta G naught prime is. It doesn't matter what all the bits are, but we can work it out from when that reaction goes, when it started to when it reaches equilibrium, the changes that we get, the equilibrium constant, can tell us what delta G naught prime is. We need to just a question. We need to finish the lecture by looking at molecules of interest, the things that we're going to be talking about in the next few weeks, whenever I am here. And the first one, of course, is ATP, adenosine triphosphate, and its related molecules, ADP and AMP, adenosine diphosphate, adenosine monophosphate. Its function is to act as an energy carrier in the cell. Energy is taken to where it's required by moving around ATP to where it's needed. It's relatively easy to make and liberates useful amounts of energy when it's hydrolyzed. You might see in the book, and it's wrong, when it says it's a high energy compound. It's not a high energy compound. It's in the middle. There are some that are a lot higher, some that are a lot lower. Why? Let's think about it. If we're a molecule that's easy to make, right? So we'll go to a higher energy level. It's very easy to make. But we don't get much energy out. We get a bit of noise. Right? If it's a bit harder to make, right, but somewhere in the middle, about there, we get more energy out, it'll be noisier, we get more energy out. Right? But it's not too hard to make, and too bad getting up there. But we get more energy out when energy is released. If it's really hard to make, I need a volunteer. What you get now? Last year, I decided that this is the last time I'm going to do this, of jumping off, because I thought, no, I'm getting older now, you know, and jumping from there, whilst, you know, you get the idea, I'm not going to do it this time. I was going to get a volunteer. Volunteer. Yeah, come on, come here. Come here. Come here. hold it tight. No. You get I am getting older, and it doesn't do the joints anymore. But the point is, ATP is sort of not there on this one, not there on that one, that high energy, even though you get more energy out, it's harder to make. It's down at this level because you know, it's relatively easy to make, but you get a useful amount of energy coming out. But why? Why does that energy come out when you use ATP? So in the ATP molecule, there are 4 negative charges. We'll read the words and then we'll see. There are 2 things. There are 4 negative charges that are close together, and there is also what's called opposing resonance, where the electrons on the oxygen that's in there doesn't know quite where to go. And when it's hydrolyzed to ADP, it loses one of the phosphates. These stresses are reduced. Okay? So delta G naught prime, the change in Gibbs free energy, is minus, does that mean energy is released or required? When it's hydrolyzed, energy is released, minus 33 kilojoules per mole. Different cell, if you look in a book, it may say 31 or 30.8 or 32 or whatever. It depends on the cell. But that's about the value. It depends on what the cell is doing and the conditions in the cell. But that's about the value that we'll take. About 33 kilojoules per mole are released when it is hydrolyzed. So if we look at the molecule, here is the adenine ring. Doesn't really matter. When you're talking about DNA, of course, is it good? Is it? Well, you know, it's a blank screen. Why don't we go like that? It works a lot better when you listen to me. So, if you're talking about DNA, of course, that's the bit that matters. What are the bases in DNA? Give me the letters. A, T, C and G. And that's the bit that matters. In DNA, the rest of the molecule, the phosphate, you know, just joins it all together. But from an energetic point of view, that bit doesn't matter at all. The adenine ring, there's a ribose sugar, and the 3 phosphate groups. And as we said, that there are a lot of negative charge here. There's 1 phosphate here, 1 here, and here. This one's got a negative charge, this one's got a negative charge, this one's got a 2 negative charges there. So we've got an awful lot of negative charge together. So, here are, pretend this is another electron, here, right, are 3 phosphates with a negative charge. And there, and 2 at the end, right? And these are linked together. Get closer together. Get closer together. All the negative charges, so people can see. Right? And because of all this negative charge that's so close together, what happens to negative charge? Yeah, it tries and repels, right? It doesn't like getting close together. Get close together. Get the negative charge together. Get together. The stress on their faces at the moment. I don't like doing this. But you can see, when you hydrolyse this one, and we lose the phosphate, give 1 negative charge over there. No, that's it. And we lose that one. This has now moved away. That's been hydrolyzed. The amount of charge is much less, and it is the stresses in the molecule are reduced. So it's all that negative charge together that is the problem. So if we can reduce that, then we've done. You know, that's why energy is released. The other thing we said was opposing resonance, and that there's a pair of electrons between the phosphate, between the oxygens in the phosphate, and it gets a bit tall, right? Here's a pair of electrons. Here's these 2 electrons. Here's one part of the molecule, here's another part of the molecule. Right? Keep these together, keep these together. No. But the electrons, you've got to keep them together. No. Don't give them up. Don't give them up. No, keep them together, but don't give them up. on tight, woman. These electrons don't know where to go. Right, no, they're over there, they're over there, they're over there. If we can break that bond, we've reduced the stresses and energy is released. So it's these two things, all that negative charge together and having these electrons that don't quite know where to go is the source of the energy in our molecule. So that's one molecule. So, have I got to learn the structure of ATP? Well, Caroline, who talks about DNA, she talk about DNA and things? Yeah. She might want you to know about the adenine ring. Do I care? No. I couldn't get that adenine ring. But what is it that the important bit from an energetics point of view are the three phosphates over there? The second sort of molecule that we need to be aware of, because this will crop up in subsequent weeks. Are we okay now? Have we stopped talking? Are we going to stop talking? Good. Yeah. Just because this is a different module, the rules about what you can do in lectures is no different in cell biology, or my lectures, in cell biology and here. Right? I'll still shout at you. I'll still throw you out if you keep talking. Let's pretend it's cell biology. We're over in Regent Street. Were we in Regent Street? No. Or wherever, where it doesn't matter where we were. But the rules are the same. Oh, what's I going to say? Acyl phosphates. Inorganic phosphate, that last component of the ATP, that's the bit that we need to add on. With acyl phosphates, we can use, these are molecules that contain a phosphate, and that phosphate can be passed directly to ADP to make ATP. And that's an example of what's called substrate level phosphorylation. So, this is no longer an electron, this is a phosphate. I am an acyl phosphate because I've got a phosphate attached here. So it's a small molecule with a phosphate attached here. Here is an ADP, right? And what do you want to become? What do you want to become? What, no, not yet. What do you want to become? Are you going to add on a phosphate to you, ADP, you're going to become ATP, right? So in substrate level phosphorylation, we get the direct transfer of this phosphate group to ADP to make ATP. Right? So that's substrate level phosphorylation, this direct transfer of a phosphate from the molecule to ADP. And an example that we'll come across in the processes of glycolysis is the reaction of this molecule called 1,3-bisphosphoglycerate. That's an example of an acyl phosphate. And delta G naught prime is minus 49 kilojoules per mole. How much energy do we need to make an ATP? 33. So is there enough there? More than enough, right? So there's more than enough energy when that 1,3-bisphosphoglycerate is used to make an ATP. There's more than enough energy is released to make the ATP and a bit left over. So here is, we say, 1, 3, the two phosphates there. This 3-carbon molecule, 1 carbon there, 1 there, 1 there. So 1 phosphate is attached there, 1 phosphate attached there. This phosphate is added to ADP to make ATP, and so the phosphate has gone from there. So this phosphate's added on to ADP to make ATP, and so we go from the 2 phosphates in this molecule to just the 1 there. Another example of substrate level phosphorylation, again in glycolysis, are called the enoyl phosphates. The enoyl phosphates. And there we have the conversion of phosphoenol pyruvate to the compound pyruvate. So phosphoenol pyruvate is converted to pyruvate in glycolysis that we'll talk about next week. But the value of delta G naught prime here is minus 62 kilojoules per mole. Is there enough to make an ATP? Is there enough to make 2 ATPs? Nearly. Oh, so nearly you could make 2. But you can only make 1, and that The rest of the energy comes out as waste heat, for example. So, delta G naught prime minus 62 kilojoules per mole, enough to make 1 ATP and a bit left, well, quite a lot left over. So that's another example of how you can make ATP just in glycolysis. Acyl phosphates, enoyl phosphates, both involved in substrate level phosphorylation. So here is phosphoenol pyruvate. 3 carbons, there, there, and there. The phosphate is attached in this middle carbon. So that phosphate is added to ADP to make ATP, and we get this compound pyruvate, which has got CH3, C double bond O, COO minus there. Right? So that's the end of glycolysis. Right at the end of glycolysis is that reaction, phosphoenol pyruvate being converted to pyruvate. Other molecules that we need to be aware of are what's called thioesters. Something's a thio compound. 3? No. Thio. That's not a number. I'll give you a clue. It's not a number. Something to do with something else, not a number. Thymine? No. Sodium thiosulfate, you want. That's a no then. Thio compounds have got a sulfur. Anybody know that? Yeah, yeah. Thio. Yeah, yeah, you knew that. Who said yeah? Who said yeah? Someone said yeah. No, it wasn't. It was a man. Unless you've got a very deep voice, it was a man. And it certainly wasn't him. He said it, right. Why didn't you shout out earlier then? You didn't just remember it now. It's because you weren't sure and you had all these people in front of you and you didn't want to shout out in case you were wrong. As you get older, you worry less about what they all think. I can assure you. You'll find out in 30 years' time. You won't care at all. You do 30 years' time, you just shout it out. Sulfur. So thio compounds contain sulfur, is what I'm saying. And as you get older, you care less what people think. That's just a thing of getting older. But the major thiol in biology is coenzyme A. And this carries an acyl group, particularly the acetyl group. So we often come across acetyl coenzyme A, C. Coenzyme A is there. Do I care about all this? No. Which is the bit that's important? The SH group there. That's the bit, that SH group there, reacts with, for example, pyruvic acid to lose one of the carbons as CO2, and we have these 2 carbons here, this acetyl group made, that's carried on coenzyme A. So CoA carries acyl groups around, right? Let's say here's a reaction that requires the acetyl group, right? Here is the acetyl group. We need CoA to carry it around the cell to take it from wherever it's being made to where it's being required, and then it gives over. So coenzyme A carries acyl groups, particularly the acetyl group, around. So all it does is carry it around to where it's required. And it's that bit at the end, that SH bit, that reacts with the acetyl group. Rest of it, I don't care. You may look, well, oh, that looks familiar, and that bit looks familiar, and whatever, and it will do, but it's the bit at the end is where it reacts. So have you got to learn the structure of CoA? No. Have you got to know at the end of it there's an SH group? Yes. The other 2 things that we'll finish with are this molecule, nicotinamide adenine dinucleotide, and there are 2 similar versions of that molecule. The first one, NAD, nicotinamide adenine dinucleotide, and that's the oxidized form of the molecule. It can bind an electron and it can be reduced. So if here is NAD, it's got an electron, it's reduced. It can give up the electron and it becomes oxidized. It can pick up another electron and become reduced. And it can become oxidized. Or it can get another electron and it become reduced. And it can give it up and become oxidized. Okay? So it carries electrons around. NAD carries electrons around. In fact, it accepts 2 electrons, but I wouldn't dare try throwing 2 electrons at the same time. It would have been a disaster. It carries 2 electrons and a proton, so it's a carrier of reducing power. NADPH is a phosphate attached, however. So here's NAD, let's add on a phosphate, and let's add it on, are you right hand or left? You're right hand. So let's put this in this phosphate. Here is a phosphate, because the cell needs to be able to differentiate between NAD and NADP. And the difference between them is a phosphate. Here's a phosphate. So, hold that. Fine, hold that. Right? We can see this is now NADP. Right? So that's where the phosphate is. This is the bit that binds electrons. Who thinks this is going to work? You've got to catch this one-handed, right? Right? Sure? They're all watching. They're all watching. No pressure. You know? This is the crescendo of the lecture. We're reaching the, they're all there looking, ready to go and whatever. If you drop it, we have a problem. So we've now got NADP, and we know it's NADP because there's a phosphate attached there. Nothing to do with where the electrons are. That's over there. Ready? So let's see if we can reduce this NADP. Shall we have another try? So here's NADP, and this is where the electrons attach. Nothing to do with the phosphate, right? Oh, come on. Ready? Yeah! So now we form that reduced form of NADP, NADPH, because it binds an electron, 2 electrons, and a proton. When NADH, why is this important? If we use NADH, those electrons from NADH, and put those into the electron transport chain of mitochondria, and in cell biology, did we do mitochondria? Yeah, we know about mitochondria and the electron transport chain. If we oxidize in mitochondria using oxygen, then delta G naught prime, the energy that's released, is minus 220 kilojoules per mole. So when you are, let's do what we probably do, and have 2 electrons, right? So we can have those 2 electrons there. Put the phosphate down. Another phosphate. If NADH uses those, or gives up those electrons, those 2 electrons, wait a minute. Those 2 electrons in the electron transport chain that's here on the front row down to oxygen, right? So here is some oxygen. This holds oxygen. Here is oxygen. If those electrons are released down the electron transport chain to oxygen, there, got them passed to oxygen, we get 220 kilojoules per mole of energy out. How many ATPs can we make out of 220? If we get, how many could we make? If we need 33 for each one. Try and do it without a calculator. About 6, 6 times 33. It's 198, which is a bit under the 220. So potentially, the amount of energy that's released, we could get 6 molecules of ATP out of it. In reality, we only get 3. And why, we'll talk about in the future. Or about 3, let's say. So, when NADH is oxidised, it gives, by oxygen, it gives us 3 ATPs. So here is NADH, or NADPH. This part of the molecule is where the electrons bind over here. The phosphate in NADPH is here. So, it's a long way from where the phosphate's nothing to do with binding electrons. It's a tag for the cell to realise there's a difference between them, right? They both carry electrons, but NADPH is a tag for the phosphate is a tag, so the cell knows there is a difference between them because it's going to be used in different reactions. So here's the nicotinamide ring, ribose sugar, phosphate, ribose sugar, adenine. Our final molecule is FAD, flavin adenine dinucleotide, which is very similar to NADH in that it carries electrons. So FAD can be reduced by binding 2 electrons and 2 protons to form the reduced form FADH2. And the molecule has similar functions to NAD. It carries electrons. The nicotinamide ring is replaced by a different ring structure, a flavin ring. And delta G naught prime is minus 180 kilojoules per mole. How many ATPs could we make? Yeah, about 5. In reality, we make 2, because it's not 100% efficient. The amount of energy, if we were 100% efficient, we'd get more ATP out of it, but we're not. So we make 2 molecules from the flavin ring. So here is FADH2. Again, it's this bit of the flavin ring that binds the electrons. The changes that you get in the molecule, whether it's oxidised or reduced, are along here. So in summary, cells need energy, precursor metabolites, these 3 or 4 or 5 or 6 carbon molecules, and reducing power. They need electrons. Catabolism, energy-releasing reactions, and anabolism, energy-requiring reactions, are linked. Gibbs free energy tells us how much useful work can be obtained. ATP is the energy carrier in the cell. Acyl phosphates and enol phosphates make ATP by substrate level phosphorylation, and NADH, NADPH, and FADH2 carry electrons. Let's stop there. Partly with Caroline on next. So next week we will carry on this. So don't think, oh, we've done NADH and whatever. Please don't forget about it, because we will be talking about it again. Okay. I wasn't standing here waiting for a I was about to say, do you have any questions? But don't turn down the door. Right, we'll take 5 minutes.